Boldly going where no science show has gone before. The Naked Scientists.
Hello and welcome to The Naked Scientists. I'm Helen Scales, and this week I'm taking the show underwater to explore my favourite realm. It's big, it's blue, it's where life began, and life certainly wouldn't be the same without it. Yes, that's right, it's the sea. Chris and the rest of the team have left me in charge and let me loose in the Naked Scientists archive, where I've been rummaging around and hunting down some of my favourite bits from past shows. So I'm afraid there are no prizes for guessing that there will be an abundance of fish, turtles, jellyfish, plus all sorts of other marine creatures swimming through this week's edition of the Naked Scientists. Among my marine menagerie, we'll be revisiting the incredible story of the squid that see not just with their eyes, but all along their bodies too. We'll once again meet the humming toadfish, a great little fish that is teaching us a thing or two about making music. We'll catch up with the clownfish that, just like Nemo, might soon need some help finding their way home. And we'll uncover the secret that giant sharks have been keeping from us for a long time. Where do they spend their winter holidays? We'll also hear about some of the problems that the oceans are facing today and how scientists are working on understanding and tackling those issues, including what goes on at the seabed when a trawl boat passes through, dragging a huge heavy net behind it. We'll be diving into the depths to find out. All that and lots more coming up on this week's watery Naked Scientists. But if you have any comments or questions about my marine mixtape, you can send us an email to chris@thenakedscientist.com.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now let's kick things off with one of my top science news stories from the past few months, and that was how scientists have solved a long-standing aquatic conundrum. One of the largest animals in the world is the giant basking shark, the second largest shark in the world. And how on earth do you think you might lose one of these creatures? Well, that is exactly what has happened up until very recently. We've had no idea at all where basking sharks disappear to in the winter, because they disappear from the waters of the West Atlantic and also in other parts of their range in the east. And no one knew where they went until Gregory Skomal from the Massachusetts Division of Marine Fisheries in the US led a team of scientists who went out and tagged 25 of these great giants off the New England coast.
Let me guess, they're down the back of the sofa. That's where everything goes.
It probably, in a way, yes, the ocean equivalent of the back of the sofa. No, sorry, Kat. But it's actually, they found them swimming thousands of miles to the south into the tropics, which is another great big revelation, really, because we always thought before that basking sharks only lived in cooler, temperate waters, and now they've been found in the Caribbean Sea. Some of them even crossed over the equator into the Amazon River basin on the coast of Brazil. And we know all this because these satellite tags that they had been tagged with, I suppose, yes, were beaming back all this information and showing where these creatures were going to. And no, not down the back of the sofa, but in parts of the world where we really haven't seen them before. And the big question is, the big mystery is, why are they going all that way? It's an awfully long way to go. Well, the researchers think it's something to do with temperature, something to do with food availability, maybe. That's one of the theories. But then why do they keep going on past Florida? Because once they get to Florida, it's nice and warm. There's lots of food for them in the wintertime, and that's the plankton. These aren't scary creatures that are going to eat you. Basking sharks eat tiny, tiny creatures called plankton and zooplankton. So maybe there's something else going on, and it could be that these sharks are going down there to breed. We have absolutely no idea where basking sharks breed. Scientists have never described an embryonic or young basking shark, which I think is extraordinary. These things really are mysterious, but it could be that they're going down there to breed, but we really don't know. And this really sheds some light on the fact that, these creatures are hugely mysterious, still a lot we need to learn about them, and also possibly how we treat them in terms of how we might want to conserve them and protect them. They are threatened, and they're listed as being vulnerable to extinction, and now maybe they're all part of one big population. Before we thought they were smaller populations that were maybe isolated from each other, but perhaps they're all intermingling, and that really will affect how we might want to go about perhaps a global basking shark conservation programme is now needed. Well, I'm still waiting to see my first basking shark, although I mustn't complain because I've been lucky enough to swim with whale sharks, which are even bigger, the biggest fish in the sea, and they're really quite an unforgettable sight. Staying with underwater discoveries, another story I covered not long ago was about how it seems that squid have turned their entire body into a giant eyeball. This is a paper that's been published in the journal PNAS this week by researchers from the University of Wisconsin-Madison in the States. And they've been looking at the underside of a Hawaiian bobtail squid. And these are really cute. Seriously, check out a picture of them. They're about 3 centimetres or an inch long. And as far as squid go, they are really quite gorgeous little things. And what they have is on their ink sac, which normally just releases ink when they want to stun predators or confuse them when something's come to eat them, they actually also glow. And the reason they do that is because of something which is known as counter-illumination. When a predator looks up at that squid from the underside, normally it would see a very dark outline against the brightness of the surface of the water. But in fact, when they glow like that, it means that they blend in. Really, they don't show up as a dark shadow against the surface of the water. And now Margaret McFarlane-Guy and her team have found evidence that those camouflage organs in the ink sacs are actually capable of not just emitting but also detecting light as well.
That's really incredible. I mean, this sort of camouflage is amazing, to be able to cancel out your own shadow, to mean that things underneath you just can't tell you're there. But how does it work? How do the squid make that light?
Well, it comes out of a type of bacteria called Vibrio fischeri, and that was discovered about 20 years ago. And they naturally glow. And this is in a process called bioluminescence. And it's a really good example of a symbiotic relationship in which two species live together and they both benefit from the arrangement. The squid have this wonderful camouflage that the bacteria give them, sort of an invisibility cloak, if you like, if you're a Harry Potter fan. And in return, the bacteria get a nice, safe place to live and with all the nutrients that they need.
Right, but surely if it's a different animal, as it were, or bacteria, then that will produce light regardless, because that's what it does. But how does the squid control it? Surely the squid needs to regulate that light.
Yes, they're not just glowing all the time. And in fact, the tissues around the ink sac that contain these bacteria actually have the ability to kind of close in around them. That's very much like an eye. It's quite extraordinary. Like the iris in your eye can change how much light gets in. This is actually controlling how much light gets out. And they're even covered over the top of the ink sac with a rudimentary lens, a clear layer. And that even kind of focuses the light a bit like a lens in your eye. So the squid really are able to match themselves very carefully to the brightness of the sea surface, because that'll change with the time of day and where they are in the world and so on.
Well, I guess it makes sense, because if they need to know how bright it is around them in order to know how to cancel out their shadow, it makes sense that these bits can also detect light as well as emit it.
Yeah, that's absolutely right. And what these researchers have done is they looked at those ink sac tissues and they found that there are genes in those tissues that are also associated, that produce proteins that we also find in eyes that are really associated with light detection in the retina. And they also looked at these light organs and they shone light at them and measured the response with an electroretinogram. And that's basically an electrode that you'd normally measure the response of a retina when light is shone on it. But they did the same thing with these ink sac tissues and found that very similar electric signals were also generated by these light organs in the squid. And that gives a really good indication that not only are they producing light from these bacteria that they're living with, but they are actually sensitive to light as well.
So could this actually tell us a bit about how vision evolved?
It certainly could, and I think the researchers at the moment don't really know exactly how the eyes of a squid are related to these ink sac structures and how that came about, but it could be a form of something called evolutionary or genetic tinkering, and that's a technical term. I think that's wonderful. And that's really sort of the co-opting of an existing system, an existing set of proteins and so on that are working to produce a certain effect, in this case capturing light. And that could be what's going on, but we do need more studies to delve a bit deeper into exactly how it is that squid have eyes and they also have this ability to detect light all the way along the bottom. And I think it also gives us some insight into this symbiotic relationship with bacteria, because we are also big animals that have a very intimate relationship with lots of bugs, because 8 out of 10, in fact, of our internal major organs have some sort of bacteria living in them. They might not produce shining light. That might be quite fun if they did, but we do rely on them and they do keep us healthy. So understanding more about how different animals and species have lived together and evolved to live together is really quite important for understanding our own health, I think. Yes, what a nice thought. All those bugs living inside us. Next up is another sea creature that hit the science news headlines recently and reminded us not only that life began in the sea, but that the first animals with backbones also first evolved underwater. And it's their modern-day descendants who are providing amazing insight into an important human trait, namely our ability to sing and make lovely, and for some of us less lovely, sounds. Now, if you like to warble in the shower or in the bath, then you probably don't realise that you're actually taking a very close step back to the origins of where your singing talent came from in the first place, and that's namely fish. This is according to a team of neuroscientists from Cornell University in the States, led by Andrew Bass, and they've discovered that...
Andrew Bass?
Oh, Kat, I thought I'd get away with that.
Andrew Bass, the fish researcher.
Hey, my name's Helen Scales and I'm a marine biologist, so what can you say? Anyway... This Andrew Bass, Professor Bass, has discovered that vertebrate brains may have been wired up for making sounds for an awfully long time, in fact for hundreds of millions of years, since the time before vertebrates hauled themselves out onto dry land. Now, the team studied the brain development of a lovely type of fish that lives along the seabed in the Pacific coast of North America, and it's called the midshipman, or I think rather wonderfully, the humming toadfish, which is nice. And the reason they're called that is because the male humming toadfish spend long hours lovingly humming away, serenading the females, trying to persuade them to lay their eggs, where they look after them in nests. So what they did was they basically injected fluorescent dyes into the growing brain cells of these toadfish larvae and watched them under microscopes as clusters of cells formed connections and started growing into the neural networks that control the fish's vocalisation. And by looking at the equivalent parts of the brain, the team discovered remarkable similarity in the neural circuits controlling similar sound making in amphibians, in birds, and also in mammals, including in primates, which really bolsters the idea, which was actually first put forward by Charles Darwin himself a long time ago. He had this thought, but couldn't prove it at all, but that really the ability to make and control sounds evolved a very, very long time ago in vertebrates, when they were still swimming around in the sea. Isn't it incredible what we can learn about ourselves by looking way back into the past at our ancestors and what they were up to millions of years ago?
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists. I'm Helen Scales, and this week we're delving into my watery picks from past shows. Coming up, we'll be hearing about some of the advanced technologies that are being deployed to help study the oceans, from electronic tags to keep tab on squishy jellyfish as they drift around the oceans, to miniature versions of the Death Star patrolling oceans far, far away. But first, we hear a lot these days in the press about climate change, what's causing it, what we can do to stop it, and how it may be changing the temperature and weather systems around the world. But one of the major implications that doesn't get so much coverage is the effect increasing levels of carbon dioxide will have on the oceans. Not just because the world will get warmer and sea levels are likely to rise, but also because a huge proportion of the CO2 that we're putting into the atmosphere ends up dissolved in the oceans, making them more acidic. Now that makes conditions increasingly tricky for many of the things that live there, and that goes for a famous fish who made it big in Hollywood. If you've seen the movie Finding Nemo, you'll know that Nemo the clownfish got lost and he had to try and find his way back home, back to his home reef. And now it seems that the Disney animators might have been onto something, because a study published in the journal PNAS, led by Philip Munday from James Cook University in Queensland, Australia, found that clownfish may indeed get lost if the oceans become more acidic. And that's likely to happen as more carbon dioxide enters the atmosphere and dissolves in the sea, forming carbonic acid. Now, we already know that many coral reef fish spend the first few weeks of life as teeny tiny larvae drifting in the open ocean. And we also know that they then follow their noses and their ears, sniffing out and listening to the sounds that lead them back to the reefs where they were born, which is, I think, another incredible part of nature. Absolutely wonderful. But the problem is, it now seems that as the acidity of seawater increases, fish might actually lose their sense of smell and have trouble finding their way home. Now, Munday and his team looked at newly hatched clownfish larvae. They put them in the laboratory and gave them a choice of swimming in water in a tank that was containing two different chemicals. And in seawater of normal acidity, the clownfish preferred to swim in a plume of water that smelt of rainforest trees, which you might say, why on earth would they do that? But in the wild, they actually tend to live on reefs that surround vegetated islands. So by following the smell of the rainforest trees, that would take them back to their homes. What happened was, when they increased the acidity in these laboratory conditions, the clownfish instead chose to swim in a plume of water that smelled of swamps. A nasty smell, actually, that we would all avoid, but certainly clownfish normally avoid these types of smells. Now, it might not sound like a huge difference, swamps or rainforests, but if wild fish really start to lose their ability to find the right sort of habitat, it could really spell disaster for entire populations and ecosystems. So I'm afraid this study really spells out another gloomy forecast for the changes we might see as carbon dioxide continues to build up in the atmosphere. We already know that since the Industrial Revolution 200 or so years ago, the acidity of the oceans has gone up. That means the pH has gone down. And it's likely to continue that way if we carry on business as usual and don't tackle that problem of greenhouse gas emissions. And it might not just mean that clownfish and other coral reef fish get lost, but it could upset entire ecosystems. While we're on the topic of turning the oceans more acidic, here's one of my favourite episodes of Kitchen Science, when Ben and Dave set out to learn more about how the chemistry of water changes when it's made fizzy with carbon dioxide. They had a bit of a 70s revival and dusted down an old soda siphon, that gadget that you'll probably find lurking at the back of a cupboard. I used to love making my own fizzy drinks with a soda stream, and I added a disgusting luminous green colouring to mine. It was supposed to be lime, but I'm really not quite sure what was going on there. Anyway, let's listen again to what Ben and Dave got up to with this piece of vintage kitchen paraphernalia.
For this week's watery kitchen science, Dave is going to show me something to do with what happens when water becomes fizzy. So, Dave, what are you going to do?
Well, I want to try and compare the chemistry of water before and after it's been made fizzy. Now, you could do this by comparing just some fizzy water you've bought in the shop and some not fizzy water, but then it's rather hard to be sure that they start off with the same kind of water. So we're going to start off with a bottle of perfectly normal tap water. It's Cambridge tap water, so it's quite hard, there's quite a lot of dissolved limestone in there. And then we're going to put it into a soda siphon and make it fizzy.
Now, soda siphon is one of these things that I've never actually seen in the flesh before. I've only seen them in 50s slapstick films where people get sprayed in the face. This is actually what you use to make the water fizzy.
Yeah, it was a very 60s, 70s thing. Basically, it's an aluminium bottle with a thing on the top with a few valves in it. You then take one of these things. It's basically a metal bulb full of very high-pressure carbon dioxide gas. You then attach it to the soda siphon and let the gas from the bulb into the water inside the bottle. That will then dissolve and you end up with fizzy water. In fact, you can do the same experiment using a soda stream rather than a soda siphon because it works in exactly the same way.
So this means that we can easily compare tap water to exactly the same tap water, just with some fizz added. But how are we actually going to test it? How are we going to see what's different?
What I've got here is some red cabbage, which I've grated up and mushed around with a spoon in some water. And then that produces this purpley liquid with some cabbage in there still. As you can see, it makes a lovely smell.
It does smell very, very strong, but it's really dark. It looks almost like ink. You can hardly see through it at all. And it's a really rich, dark blue, sort of purple type colour.
Yeah, that's right. This colour is coming from a dye, which is a type of anthocyanin. Now, these are dyes which are found all over the natural world, from red roses to bluebells. And this dye is also what you find in litmus paper. It's a litmus dye. And it will change colour depending on how acid its environment is. And
you've mushed that up in just the same water that we're testing to see what happens when it gets fizzy.
That's right. Cambridge water is slightly alkaline, so at the moment it should have a slightly bluish, purplish tinge.
Does this mean that if you were to do the same experiment with water from somewhere else, that it might not be the same colour?
Yes, if you did it from a soft water area, it would probably be reddish in tinge. And actually, we want to start it off slightly bluish. So if you live in a soft water area and it starts off slightly reddish, add a little bit of bicarbonate of soda until it just starts to be a bluey, purpley colour.
OK, so we start off with this really nice, inky, purple-blue colour. And what are we actually going to do?
I've got 2 glasses here. I'm going to put maybe a few millimetres, 3 or 4 millimetres of this strong red cabbage solution into the bottom of each glass.
OK, well, certainly the smell of cabbage is filling the room, which just isn't very nice. But we now have red cabbage solution in the bottom of each glass. So when we come back later in the show, what are we going to use this for?
We're going to add some tap water to 1 glass. And then we're going to take the same tap water, put it into the soda siphon, carbonate it, add lots of carbon dioxide, then squirt it into the other glass and see if there's any difference.
OK, so when we come back into the show, we're going to do a very well-controlled test to find out if there's any difference in the acidity between some normal tap water or some tap water that's been made fizzy. We'll be back later in the show.
So, can you remember what happened when Ben and Dave were messing around with cabbage indicator and a soda stream? We'll get back to them later on in the show to tell us once again what happened and what it tells us about carbon dioxide and the oceans.
Laying the facts bare. The Naked Scientists.
Now, one of the most obvious things about the oceans is how huge they are. They cover 7/10 of the Earth, and it's undeniably true that we do indeed live on a blue planet. But because of all that water, it's rather difficult to keep track of all the animals that live in it, especially animals like some of my absolute favourite underwater creatures, the sea turtles, and they spend their lives swimming huge distances across entire ocean basins. Now, one way of learning more about the secret lives of turtles is by following the oceanic movements, not of the turtles themselves, but of their favourite food, the jellyfish. But just how do you keep track of those transparent, slippery animals? Ben spoke to John Horton to find out.
And also in the news this week, how scientists from Queen's University in Belfast are electronically tagging jellyfish. Now, presumably not just jellyfish with an ASBO, but electronically tagging any jellyfish they can catch, to help with studying turtles. Now, joining us on the line now is John Houghton. Hi, John. If you're studying turtles, why is it that you're tagging jellyfish?
Well, leatherback turtles are the ones that eat jellyfish, and they cause a bit of a problem for us because they're not like a typical migratory species that moves from one spot to another. They just fan out through the entire ocean. And so we, for a long time, haven't actually known where they were feeding or what they were feeding on. And a couple of years we did big aerial surveys of the whole Irish Sea. And what we found was not what we thought we were going to find. We thought the jellyfish would just be randomly everywhere. What we found was in like 4 or 5 main bays, you get these hundreds of thousands of giant jellyfish that are there year after year after year. And when we modelled the distribution of leatherback turtles, we actually find out that they tied up in the same place. That wouldn't be very exciting if you work on land, but when you work on an animal that lives beneath the sea and you can never blooming find it, actually just a simple thing of tying predator and prey was very good.
Now, how do these electronic tags work? I'm guessing these are not the things that report that you're not in your home when you should be.
No, but I'm not a million miles away from it. I mean, they're data storage tags, and so they're tiny anyway. They're about the size of your little finger. And the ones we're going to do this year are quite simple. They just record depth and temperature and light levels. And so we just put it onto a jellyfish. It records all the information, and then eventually we retrieve the tag.
Now, I've seen plenty of jellyfish washed up on the beach. They're very squidgy, sort of fluidy things. How on earth do you attach an electronic tag onto something that's so amorphous and blobby?
That's true. I mean, but there's jellyfish and there's jellyfish, you see, and I think the ones you're describing would be called aurelia. They're the common jellyfish, and they're tiny, and they are floppy and wobbly, and they would be almost impossible to tag. The ones we're going after are called barrel jellyfish, and they're massive. I mean, they're nearly a metre across and weigh 27, 28 kilos.
Wow.
So, and they are actually quite big, tough animals. They're very strong swimmers. They can swim against the current. And so you actually, again, if you think of a jellyfish looking like a mushroom, you've got the stalk part coming out underneath what we call the bell. Quite simply, all you do is you just tie a little time depth recorder to a plastic cable tie, swim up to the jellyfish, tie it around, and it takes about 10 seconds.
And so, does this affect their behaviour? I mean, they must not like having something stuck round their body.
I mean, they're very simple animals. I mean, they do react, that's true. I mean, we did trials off the west of Ireland last year, and not surprisingly, when you attach a tater jellyfish, it just swims straight to the seabed and tries to get away from you. But what we found that after, say, an hour or so, then it all just moves back up into the water and gets on with doing its jellyfish business. So as long as you get past those first few hours and you ignore those, then it's fine. And you're talking about a device that is, 0.1% of the whole animal's body weight, so it doesn't really affect it that much.
So how long are they going to keep these tags on? When are you expecting to get this data back?
That we don't know the answer to. I mean, the particular jellyfish we're going after, they're unusual. Most jellyfish that will boom and bust in a couple of months in the summer. These guys seem to be around all year. So we're going to put the tags on probably in August, and sure, they could be turning up any time within, say, 2 months to maybe even a year down the line. So, yeah, any time over the next year.
And how do you actually collect this data? Does it just float up from where the jellyfish were?
Yeah, what we've got attached to the time depth recorder, a little dive computer, is just a tiny fishing float. And on the fishing float is just a little label with a reward on it. So once the jellyfish dies, the whole device just disattaches itself from the jelly, floats to the surface, and we're putting them on in like big bays where we know they will wash ashore. So if you find one on the beach, just pick up the reward label and give us a call.
Fantastic. Well, thank you ever so much, John. That was John Houghton from Queen's University in Belfast explaining how tagging a jellyfish could actually teach us quite a lot about marine life.
Jellyfish are such wonderful creatures, aren't they? When I was little, I used to be quite scared of them and thought they were just ugly lumps of gooey stuff that lay stranded on the beach. But since then, I've got to know them. I've been stung a few times, I must admit, but I've seen all sorts of beautiful jellyfish underwater and all the sorts of amazing things they get up to, including, according to another recent study in Nature, they might help mix up the oceans as they swim around. You can catch that story on the Naked Scientist website. Now, I just love hearing about how the latest technology is being used to tag and track wild marine animals as we send them off to collect information for us about their own mysterious ocean home. And we don't actually have to just rely on living things to help us find out more about the vast oceans, but armies of underwater robots are also becoming a reality these days too. Here's Chris talking to Jules Jaffe, an engineer who works at the cutting edge of high-tech ocean exploration.
My name is Jules Jaffe, and I am a scientist, research oceanographer here at the Scripps Institution of Oceanography. Over the past decade, we've developed a rather large vehicle, something on the order of a Volkswagen Beetle-sized vehicle, which has the capability of adjusting its buoyancy. And on it, we put a laser and we put some very sensitive cameras, and we can put that off the ship. It weighs almost a ton, so it's hardly something you could go out on your rowboat and put in the water. We need a fairly large ship. And we've learned a lot of interesting things. But the problem we've kept coming up against with this, and it becomes more and more obvious the more we process our data and the more we think about it, is that we're just sampling one place at one time. And even though we get a nice picture from that place and time, and there are inferences we can make, we're starting to work on distributed sensor networks, where instead of having just one sampler in one place at one time, we've got sort of a small army of these things, and they're all going up and down in the water, and they're all sampling different places at different times. And if we know where they are, and we know when they're there, and we have the appropriate sensors on them, we can start to reconstruct this three-dimensional distribution of these organisms and actually look at mechanism as opposed to just looking at more or less existence.
How do you get them to talk to each other? Because a major problem with underwater communication, as submariners know very well, you can't get radio signals through water terribly easily. So how do you keep them in touch with each other?
Well, the ocean, as you've already highlighted, is particularly opaque to electromagnetic radiation. But acoustics, on the other hand, as has been known by animals that have evolved over hundreds of millions of years, can in fact go far. And so our plan is to have these vehicles localizing each other acoustically. And of course, we can communicate with one of them that is fairly close to us, and then they can distribute that message among the entire group. By relaying this information, we think we can evolve sensor systems which can sense tens of kilometers instead of maybe just hundreds of meters.
Would they be carried by ocean currents? You deploy a sort of array of these things over a certain distance and then let the natural current move them along?
Precisely, and you've actually had a wonderful insight into one of the advantages of our technology, is that we would like to be in the frame of reference of the organism itself. So when you're sitting up on a ship and the thing's bobbing up and down and you stick something in the water, that thing's going to be moving around. So we found out a long time ago that it makes more sense to put the vehicle in the water and let it sort of go with the flow, as we say, and to have maybe tens or even 100 of these things going with the flow allows us not only to take a snapshot of their evolving environment, but also to track them. And there are many enigmas in oceanography which we don't understand, having to do with small animals that, say, are born on shore, and they have a pelagic part of their life where they go out to sea, maybe for 3 months, little baby barnacle or something like that, and somehow they get back. And to be honest, I don't have an idea how they do that, and most of the people I know who study these things don't have an idea how they do that. So we can not only study this sort of 10-kilometer area, but we can watch it evolve and be sort of transported in time and maybe start to unravel some of these riddles of how organisms survive in the ocean.
This presumably is what you're actually building at the moment. Is that going to be one of these vehicles?
That's correct. So what we're looking at here, Chris, is something on the size of a soccer ball, which has been cut in half, and we're looking inside at the electronics of this device.
It looks like something that should be in Star Wars, actually, but
well,
talk us through what it is.
There's a good story about that, actually, because in our last grant proposal to the National Science Foundation, we wanted to present a color graphic of these devices, and my colleague actually took the Death Star and shrunk it down, and he created a picture where he had about 20 of these Death Stars communicating with each other. So, in fact, we're not that far away.
But is that the right message to be sending out? Because you're actually trying to save the Earth,
yeah,
not destroy
that's
it.
correct.
But how does it work?
Okay, so basically what we have here is a pretty simple thing. It's a soccer ball with a bunch of electronics inside of it, and the soccer ball is thick enough so that we can send it down to about 80 meters of depth without imploding. And the computer has sensors that tell it what the depth of the vehicle is. So by adjusting its buoyancy, its volume, in the ocean, we can actually send it down and keep it at a certain depth in the sea. And what we also have on this vehicle, on the bottom here, is an acoustic transmitter and a receiver. We call that a transducer. And it can send sound and receive sound. And these are actually modems. So they're actually communicating devices which allows these vehicles to talk to each other, and they can actually range off of each other. So that allows us, knowing their depth and knowing how far they are from each other, to estimate their three-dimensional positions. So now imagine a fleet of maybe 100 of these things, slowly descending in the sea, localizing off each other, each equipped with some method of sensing plankton density, or perhaps other things like zooplankton using acoustics. And using this 100 or so samples, time-varying samples, we can now create a three-dimensional time-varying record of the evolution of, say, a volume that might be more like 5 kilometers by 5 kilometers by this 80-meter deep, it's not a cube, but this volume.
How long does it take you to develop something like this, from concept to getting something that you can put into the Pacific out there?
Well, you've touched a very tender subject with me. So you might have noticed I have sort of a bit of comedy associated with my personality. So what I tell my students is that if you're pregnant, you're guaranteed in 9 months. But if you're an engineer and you're building a vehicle, it could be 10 years. And so we're sort of giving birth. In fact, this has been an exciting week for us because 10 years from the inception of this, we've now started to test these things in the ocean with the modem communication. And it's really exciting. But by the time I tell our students that science is not something if you want immediate gratification. Because the time you think of a thing, write the proposal, perhaps get it rejected a few times before it's funded, do the research, get the results, process the data, publish it, and go to colleagues and tell them what you've done. It can often be sort of a 7 to 10 year period.
That was underwater robot designer Jules Jaffe from the Scripps Institute at the University of San Diego, talking to Chris about his incredible miniature underwater Death Stars that, far from destroying things, are designed to find out more about life in the oceans. And we've recently heard some good news from Jules. He tells us that his research team have just been awarded a major grant from the US National Science Foundation, so they now have plans to build 6 of the soccer ball-sized sensors, or football-sized for our UK listeners, and another 20 smaller 1-litre versions. He also says that they're right in the middle of testing out a brand new idea that would make these robots buoyant enough so that they stick up at the water surface and make contact with a satellite, so the data they have can be automatically sent back to the lab. So we wish Jules and the team all the very best and look forward to hearing how the robots get on. You're listening to The Naked Scientist with me, Helen Scales, and this week we're all about the sea. Yes, that's right, I've been left in charge and I'm revisiting some of my favourite stories from past shows. We've heard about some of the wonderful animals that live in the oceans, but what about the problems facing the oceans in the 21st century? An issue that's becoming increasingly obvious is the problem of overfishing. All around the world, too much sea life is being taken away to pile onto our plates, and not enough's being left behind to sustain wild populations. And that's leading to what seems to be the inevitable and depressing emptying of the oceans. And what's even worse is when methods of fishing also leave behind a trail of destruction in their path. The main culprits are the trawl fisheries that drag heavy nets across the seafloor in deeper and deeper parts of the oceans. We sent Mira to meet Les Watling from the University of Hawaii to find out more about the problem of trawling and what can be done about it.
Well, trawling is a method of catching fish that actually started in Britain in the 14th century, where someone found out that you could, if you took a net and held it open some way and hauled it behind a boat, you could get a lot of fish, but you also get a lot of other stuff. I've actually been looking at effects of fishing for about 15 years, and I've been in submarines and I've had cameras on remote vehicles. What I generally see is that when an area has been trawled, there's not much living on the surface of the ocean floor. We know that trawls also dig into the sediment. They disrupt all kinds of things. So generally, if you go to an area that's trawled, it's really, really noticeable.
When the boats are going by, what effect is the trawling having on the seabed?
Usually what happens is anything that's standing up from the bottom, anything like a sponge or coral or something that's growing up from the bottom, that's usually bent over, broken, or removed. If it's a muddy bottom, then the gear digs into the bottom. And the important thing here is to realize that most of the animals that live in the muddy bottom live in the upper 3 or 4 centimeters. So you don't have to dig in very far before you've disrupted the burrows and tubes of all these small things.
Okay, so they've been disrupted, but then what's the impact of that? What effect does that have?
It depends. Some animals recover from this disruption okay, which means they can make a new burrow or tube. But a lot of animals that invest a huge amount of energy into making a tube. In fact, some cases, some of the marine worms, for example, they've lost the ability to remake a tube. So then that's it. Then they are laying on the surface and they could be eaten by a fish or any other thing that comes along. So they've lost their protection, as it were. Other animals raise their young in their burrows and tubes, and if that's destroyed, then the babies may not be able to burrow their way out of this mud that's been stirred up. So we tend to see species in these trawled areas that have really high reproduction. They're weeds, in the best sense of the word. They have high reproduction, they can recolonize, they're capable of getting their house blown down, if you want to think of it that way, and rebuild it real fast, all that sort of stuff. So you tend to lose the things that have a longer, more stable lifestyle, especially if it's an area that's trawled repeatedly. If a person drags a trawl over an area once, then a lot of things will survive that. Maybe half of the things that live there will survive that. And there will be a certain amount of recolonization that could occur in future years. But a lot of times trawling occurs over and over again in particular areas. Fishermen have their favorite spots. And when you go to those areas, you find that the whole bottom community has really changed to these weedy type species, which is, from a fish perspective, might not be so bad because a lot of fish tend to eat those weedy species too. So you could get, like flatfishes, for example. It's been shown in the North Sea that if you retrawl areas a lot, you can get flatfishes, but you might not get other kinds of fishes because their food is missing. You create a completely different bottom community and a new ecosystem, as it were. One parallel that I like to use is what happens when you go in and, as happened in North America, for example, colonists came, they cut down all the forest, and they turned it into pasture land. So you lost all of the birds that nested in the trees. So it's a very similar kind of thing. The community is still productive because now you're growing sheep or cattle or whatever, but you have lost a lot of the biodiversity that was there.
How much of the world's marine ecosystem is being affected by trawling?
Well, that's a hard estimate to make. We looked at the number of fishing vessels and where they were around the world about 10 years ago, and we figured that about half of the continental shelves of the world get trawled each year. That number is obviously fluctuating because fisheries have collapsed in a lot of these areas. And it may be the collapse of some of these continental shelf fisheries that will allow some of this biodiversity to recover.
So what do you think the solution is? What can we now aim to do, knowing this?
Well, this is going to be a little controversial. But, people have been proposing for a number of years now to set aside marine protected areas that you don't go into with any kind of gear. And these areas are generally been proposed to be about 20 or 30% of the continental shelf area around the world. We should be looking at it the other way around, that we should protect most of the sea bottom and allow trawls into only a very small percentage.
And I guess if that does happen, do you think that the effects that trawling has had so far is reversible?
It's reversible. The timescales are going to be long the deeper you go in the sea. I have a project that we just finished looking at an area that had been closed to trawling for 6 years. And it doesn't look at all anything like the areas that have never been trawled. So that's 6 years on. If you go into really deep water, we know on the seamounts, for example, that corals recruit at extremely low rates. We had a study where we were looking for coral recruits on the seamounts in the North Atlantic, and we found one on a block that had been put out, that had been out there for a year and a half.
So I guess if fishing can be reduced, the outlook is quite promising, and it's not something that's just going to be left disturbed.
Promising in the long run, yeah. For the continental shelves, for areas that have rocky, stony, marl bottoms, those, we're looking at 25 to 50 years probably for a recovery time before the big things like sponges start to regrow. The deeper you go, though, the longer. I'm certain that seamounts that have had all the corals removed from the top will not have corals again for a century or 2 centuries. This is a really long time.
Yes, that is an incredibly long time, isn't it? And it's so worrying to think that it takes just a few trawl boats to cause damage that could take ecosystems centuries to recover from. That was Mira St. Thillingham talking to Les Watling from the University of Hawaii about the deep-sea perils of trawling.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
This is a special Oceans edition of The Naked Scientists with me, Helen Scales. We'll be diving back into the science of the oceans in a few minutes, but first we continue with our special summer season of Chemistry in its Element. This week, Kira Wiseman from Saarlands University in Germany explores the element that stops eggs sticking to frying pans and keeps astronauts safe in space. But it can also be a vicious killer.
The 37-year-old technician spilled only a few hundred milliliters or so on his lap during a routine paleontology experiment. He took the normal precaution in such situations, quickly dousing himself with water from a laboratory hose, and even plunged into a nearby swimming pool while the paramedics were en route. But a week later, doctors removed a leg, and a week after that, he was dead. The culprit, hydrofluoric acid, colloquially known as HF, and the unfortunate man was not its first victim. Unlike its close relatives, hydrochloric and hydrobromic acid, HF is a weak acid. This, coupled with its small molecular size, allows it to penetrate the skin and migrate rapidly towards the deeper tissue layers. Once past the epidermis, HF starts to dissociate, unleashing the highly reactive fluoride ion. Free fluoride binds tightly to both calcium and magnesium, forming insoluble salts which precipitate into the surrounding tissues. Robbed of their cofactors, critical metabolic enzymes can no longer function. Cells begin to die, tissues to liquefy, and bone to corrode away. And if calcium loss is rapid enough, muscles such as the heart stop working. Burns with concentrated HF involving as little as 2.5% of the body's surface area, the size of the sole of the foot, for example, have been fatal. HF has a long history of destructive behavior, claiming the lives of several chemists in the 1800s, including the Belgian Paulin Lhuillier and the Frenchman Jérôme Nicle. These brave scientists were battling to be the first to isolate elemental fluorine, F2, from its various compounds using electrolysis. However, it was Nicle's countryman, Henri Moissan, who succeeded in 1886. To achieve this feat, Moissan not only had to contend with HF, the preferred electrolyte in such experiments, but fluorine itself, a violently reactive gas. His key innovation was to construct an apparatus out of platinum, one of the few metals capable of resisting attack, while cooling the electrolytic solution down to minus 50 degrees Celsius to limit corrosion. Moissan's feat earned him the 1906 Nobel Prize in Chemistry, but the celebration was short-lived. Another victim of fluorine's toxic effects, he died only 2 months later. Yet Moissan's method lived on and is used today to produce multi-ton quantities of fluorine from its ore fluorspar. Ironically, while elemental fluorine is decidedly bad for your health, fluorine atoms turn up in some 20% of all pharmaceuticals. The top-selling antidepressant Prozac, the cholesterol-lowering drug Lipitor, and the antibacterial Cipro all have fluorine to thank for their success. How is this possible? Because the flip side of fluorine's extreme reactivity is the strength of the bonds it forms with other atoms, notably including carbon. This property makes organofluorine compounds some of the most stable and inert substances known to man. Fluorine's special status also stems from the fluorine factor, the ability of this little atom to fine-tune the chemical properties of an entire molecule. For example, replacing hydrogen with fluorine can protect drugs from degradation by metabolic enzymes, extending their active lifetimes inside the body. Or the introduced fluorine can alter a molecule's shape so that it binds better to its target protein. Such precise chemical tinkering can now be carried out in pharmaceutical labs using an array of safe, commercially available fluorinating agents, or the tricky transformations can simply be outsourced to someone else. Most of us also have fluorine to thank for our beaming smiles. The cavity-fighting agents in toothpaste are inorganic fluorides such as sodium fluoride and sodium monofluorophosphate. Fluoride not only decreases the amount of enamel-dissolving acid produced by plaque bacteria, but aids in the tooth rebuilding process, insinuating itself into the enamel to form an even harder surface which resists future attack. And the list of medical applications doesn't stop there. Being put to sleep is a little bit less worrisome thanks to fluorinated anesthetics such as isoflurane and desflurane, which replaced flammable and explosive alternatives such as diethyl ether and chloroform. Fluorocarbons are also one of the leading candidates in development as artificial blood, as oxygen is more soluble in these materials than in most other solvents. And radioactive fluorine, 18F rather than the naturally occurring 19F, is a key ingredient in positron emission tomography, or PET, a whole-body imaging technique that allows cancerous tumors to be discovered before they spread. Fluorochemicals are also a mainstay of industry. One of the most famous is the polymer polytetrafluoroethylene, better known as Teflon, which holds the title of world's most slippery solid. Highly thermostable and waterproof, it's used as a coating for pots and pans, in baking sprays, and to repel stains on furniture and carpets. Heating and stretching transforms Teflon into Gore-Tex, the porous membrane of sportswear fame. Gore-Tex pores are small enough to keep water droplets out, while allowing water vapor, that is, sweat, to escape, so you can run on a rainy day and still stay dry. Fluorine plays another important role in keeping you cool, as air conditioning and household refrigeration units run on energy-efficient fluorocarbon fluids. And fluorine's uses are not limited to Earth. When astronauts jet off into space, they put their trust in fluoroelastomers, a type of fluorinated rubber. Fashioned into O-rings and other sealing devices, these materials ensure that aircraft remain leak-free, even under extreme conditions of heat and cold. And when accidents do happen, space travelers can rely on fluorocarbon-based fire extinguishers to put the flames out. Fluorine has long been known as the tiger of chemistry, and while the element certainly retains its wild side, we can reasonably claim to have tamed it. As only a handful of naturally occurring organofluorine compounds have ever been discovered, some might even argue that we now make better use of fluorine than nature herself.
That was Kira Wiseman from Saarlands University in Germany with the story of fluorine. Next week, we'll explore the properties of thallium, an element that rose to fame as the subject of an Agatha Christie murder mystery. Meanwhile, if you'd like to hear more of the stories of the elements that make up the world around us, then you can take a look at the Royal Society of Chemistry's website, which is at chemistryworld.org/elements. Now let's go back to Ben and Dave with their aquatic kitchen science and find out what happens when carbon dioxide and water are put in the mix.
Welcome back to this week's Kitchen Science, where I'm literally fizzing with anticipation to find out what the difference is in chemistry between fizzy water and normal still tap water. So Dave, can you take us through what we've got set up?
Okay, I've got some red cabbage water. That's basically just perfectly normal uncooked red cabbage mushed up in some tap water, which produces this sort of purpley coloured solution. And I've put a little bit of the solution in 2 glasses, maybe only 3 or 4 millimetres in the bottom of each glass. I'm now going to put some normal tap water in one of the 2 glasses.
Well, clearly it diluted it, and so it doesn't look as strong, it's not quite as opaque as it was before, but it's still a lovely inky purple-blue colour.
Yep, that's what you'd expect. The water in Cambridge is slightly alkaline, so it's going to produce this bluish colour.
Okay, and now we need to make some of that self-same tap water fizzy, so we're going to put it into your fantastic retro soda siphon.
That's the plan.
So how much does your soda siphon take? How much water will it hold?
Probably 2/3 of a litre or so.
And it looks as if it's made out of similar stuff to, say, a thermos flask.
This one is made out of aluminium. It just needs to be a fairly strong bottle because it's going to take quite a high pressure in a minute.
And then we have a special little canister, a bulb of CO2. Now this screws onto the side of the soda siphon, and there's a cap that goes over the top.
This cap's actually pushing it onto a little spike, a hollow spike, that pushes the spike through the end of the bulb, which lets the pressurised carbon dioxide from inside the bulb into the bottle.
And this is why it needs to be quite well built, because actually that's under quite high pressure.
It will probably go up to sort of 5 or 6 atmospheres at least, yes. Okay, so now I'm going to screw it on tight and break the seal.
That was a brilliant noise. I assume what happened there was the spike broke the seal, all of that compressed CO2 got pushed into the water. But how does that actually make it fizzy? Won't it just displace some water and sit at the top being a gas?
Well, carbon dioxide is actually quite soluble in water. And that's because carbon dioxide, CO2, will actually react with water molecules. So a CO2 molecule will react with an H2O water molecule to form H2CO3. This means you can dissolve an awful lot more CO2 gas in water than you could do other gases which don't react with water, like oxygen or nitrogen.
Why do you have to have so much pressure?
Well, this reaction is reversible. It can go in both ways. Water can react with carbon dioxide molecules, or they can split up again and the carbon dioxide can escape. This means that if you want to get lots of carbon dioxide inside the water, you have to have a lot of carbon dioxide there. So the more carbon dioxide you put above the water, the more of it's going to work its way into the water and you're going to get more dissolved and you get more carbonated water.
But what has that done to the chemistry of the water? I think we need to find out by mixing it with your cabbage solution, don't we?
Yeah, we'll try the second glass.
Wow. Well, it obviously spluttered a bit to begin with, but the colour difference is really obvious. It's pink.
Yes, and like litmus, if red cabbage water is pink, that means it's acidic. So the carbon dioxide solution is obviously acidic.
So not only have we made this water fizzy, but we've also made it more acidic. What's actually happened?
Well, there's actually another reaction going on here. The H2CO3, which we created by reacting carbon dioxide and water together, can also split up to form H pluses, 2H pluses, and CO3 minus, 2 minus. These H pluses then stick to a water molecule to form HCO plus, and these hydronium ions, as they are called, will then float around in the water. And if you've got something with lots of H plus, lots of hydronium ions, then it's an acid.
So how does the change in acidity lead to the change in colour?
Well, some of these hydrogen ions will then go and react with the anthocyanin dye molecules from the red cabbage, and they change its colour.
And so we get a change from this sort of inky blue through to this girly pink.
Yeah, that's pretty much it.
There's also CO2 in the atmosphere. In fact, we hear a great deal about how much CO2 we have put into the atmosphere since the Industrial Revolution. So does this mean that the same thing happens in our rivers, our lakes, and in the sea?
Yes, and it always has done. The carbon dioxide in the atmosphere will dissolve in water, make it slightly acidic. This acid will actually dissolve things like limestone. So water running through limestone will tend to dissolve it, and it creates caves.
But is it a problem, therefore, that we've been putting more and more CO2 into the atmosphere? As you said, the more there is above the water, the more there is that can get in.
Yeah, that's right. And in fact, the oceans are a major sink of carbon dioxide. It just dissolves in them. And as it dissolves, it will make them more acidic. Now, there has been some research which says that the more acidic the oceans get, the more carbon dioxide that's dissolved in them can start causing problems for creatures with shells made out of essentially limestone, calcite. So things like oysters and, say, corals. So even if you don't think that the carbon dioxide in the atmosphere is going to warm up the world, it's certainly going to do things to the pH of the oceans.
So making water fizzy by adding carbon dioxide also makes it more acidic, as Ben and Dave showed us there with a soda siphon and stinky red cabbage indicator. And that's the same thing that's going on in the oceans. And we already know that this spells really bad news indeed for many of the sea creatures that live inside some sort of chalky limestone shell. And that includes corals, seashells, and all sorts of phytoplankton. And those are the tiny algae that drift through the seas and play a really vital role themselves in mopping up carbon dioxide and helping to lock it away from the atmosphere. You can read all about that episode of Kitchen Science on the website at thenakedscientist.com/kitchen science, along with lots of other experiments that you can do at home. Now, how could we have a special Oceans edition of The Naked Scientist without paying a visit to Diana O'Carroll and listening again to one of her watery questions of the week? Here she is diving into a question about how sharks track down their dinner.
We've got quite a smelly question for you guys now.
My name's Vince Mills from Solihull in the West Midlands. Apparently, a shark can smell blood up to a quarter of a mile away. How does smell travel in water? It would seem strange that if you drop ink in water, it takes ages to dissipate. So how can the individual particles of a smell travel so far and apparently so fast?
So how can a shark really smell when dinner's on the table?
My name is Thomas Breithaupt and I'm lecturer in ecology at the University of Hull. Vince is absolutely right in questioning the scenario in wildlife programs where sharks apparently are attracted from a distance within a very short time after some smelly substance has been dumped in the ocean. Odor molecules in general are carried to the shark by water currents. If there are no water currents, then it is molecular diffusion, the random movement of molecules that disperses the odor away from the source. But diffusion is an extremely slow process, as Vince experienced in his ink experiment. In general, the travel time of odor depends entirely on the local water velocity. Near the water surface, water velocities in the ocean can range between a few centimeters per second on a very calm day and several meters per second in a strong current. In summary, odor can theoretically be detected by a shark over several miles from the source, and I would estimate that in the ocean a smell takes at least 1 minute to reach the shark at a distance of 100 meters. More likely it will need between 10 and 20 minutes. Finally, the shark still needs to get to the source, and that would take another 10 to 100 seconds depending on the swim speed of the shark. So if smelly things are dumped into the ocean, don't expect a shark to be attracted from a distance in less than a few minutes.
So a shark finds its dinner before it gets cold, but perhaps not as fast as some documentaries and films might have you believe.
That was Diana O'Carroll finding out that sharks may be experts at catching a whiff of food from a long way off, but it will still take them quite a while to catch up with it. And finally, how could I resist repeating an answer about one of the smaller coastal critters, but one that nonetheless is still quite well endowed?
Beverly says, how do barnacles mate with each other?
Barnacles, if you've ever been down to the shoreline, are rooted very solidly to the spot. So how do they move around and find a mate? Well, lots of other marine creatures have a similar problem. Things like corals, which are animals, they don't move either, but they solve that by sending their sperm and eggs up into the water, and hopefully they'll meet each other and fertilisation will take place and larvae will be created. But that's not what barnacles do. Barnacles look a bit like other types of mollusk on the seashore, but they are in fact a type of crustacean. So like crabs and lobsters, things like that, but very much smaller. But they do actually have sex directly, and the only way they can do that is by having a very long appendage. The male barnacles have very long penises, one of the longest in comparison to the size of the body that there is in the animal world, animal kingdom. And
It didn't include me in the analysis, just like to say that.
No comment. And the barnacle males will literally poke around next to them and see what they can find. So they don't have much reach, really, in actual terms, but they can reach out and fertilise female barnacles. So take a closer look next time you're down on the shore. And yes, most barnacles are in fact actually hermaphrodites. Each one is both male and female at the same time, so they both have that incredible long penis, up to 8 times their body length, and also a set of female sex organs as well. But they do have to mate, they can't just fertilise themselves. And in fact, leading on from that question, there was an interesting study published last year by Chris Neufeld and Robert Palmer from the Banfield Marine Sciences Centre on Vancouver Island in Canada, and they were looking at the anatomy of barnacles living in different environments. And they discovered that when barnacles live in calm, sheltered shores, they have longer, thinner penises, compared to males living on shores exposed to lots of wave action. Now, it seems that when water's moving around and there's lots of strong current, it's easier to manoeuvre a shorter, stouter appendage. And when conditions are calm, it pays to have a longer, thinner penis, so that each barnacle can reach more mates. And most interestingly, Neufeld and Palmer transplanted barnacles from an exposed to a sheltered shore, and they found that individuals could change the dimensions of their male members to suit their surroundings. Yes, aren't those barnacles really something? So many thanks again to everyone who's already sent in questions, and do keep them coming in. The email address, as always, is chris@thenakedscientist.com. And if this week's show has whetted your appetite for more fishy matters, then you might like to check out my new book that I've been working really hard on, and it finally hits the shelves this August. It's called Poseidon's Steed, and you might have guessed it's about those mysterious, beautiful denizens of the deep, the seahorses. It's packed full of all sorts of interesting seahorse science. I've hunted down answers to all sorts of questions like, why do they look so strange? How did they evolve? And the ultimate question, out of all of the millions of animal species that there are in the world, why are the seahorses the only males that get pregnant and give birth? What can the seahorses tell us about what it means to be male? Well, there's something in there for everyone, from plundered treasure and magical potions. Did you know seahorses were once used as a cure for baldness? To ancient artwork, cartoon characters, pop songs and aquariums. Have a look at my website, helenscales.com, for more details. And if you do fancy having a read, I'd love to hear what you think. Now that's just about all we've got time for this week. It just remains for me to say a big thank you once again to John Horton, Jules Jaffe and Les Watling, and to our production team, Ben Valsler, Dave Ansell, Mira Sinthalingham, Laura Soul and Diana O'Carroll. Tune in next week to hear Ben and Dave's best bits. They'll be bringing us some homemade steam engines, chocolate teapots and some explosive chemistry experiments with Brighton University's Dr. Hal. But for now, thanks for listening and goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.